Okay, gang, today we're going to be talking about dynamic equilibrium and how we could represent objects in dynamic equilibrium using position versus time graphs. This PowerPoint is going to go along with the hallway carts lab investigation that you did. First, remember when we say an object is in dynamic equilibrium, what we mean is that the forces are balanced and that that object is moving at a constant velocity. Furthermore, understand that velocity is telling us how fast the object is moving, as well as the direction that it is moving in. So an object that is in dynamic equilibrium moves at a constant speed in a constant direction. When you guys did your hallway carts lab activity, you should have gotten a position versus time graph for each of the 4 carts that looks like this. Also, remember, cart number 3 was a little bit different than the other 3 carts in this activity. For that motion, we had the cart have a little bit of a delayed start, where it wasn't moving for the first 3 seconds, and then it began moving at a constant velocity like all of the other carts. So the fit for cart number 3 should look a little bit like that. That first segment that you see there is where the object is in static equilibrium. There's a lot of information that we can gather just by looking at a position versus time graph. First off, we could tell exactly where the starting position of each of these carts is. The initial position is represented by the y-intercept value of the graph. So for instance, notice for cart number 1 at 0 seconds, or the y-intercept, the position was 0 meters. For cart number 2, the y-intercept value is 2 meters, meaning the initial position is 2. For cart number 3, the initial position is 3 meters. And cart number 4, the initial position is all the way up at 8 meters. Second, how can we tell exactly how fast each cart is moving? Well, qualitatively, we could just compare the slope of each of these lines. The velocity represents the slope of this graph. Therefore, the steeper the slope, the faster the object is moving. If I compare the slope of line of the cart for number 1 and the slope of the line for cart number 2, we notice that cart number 2's slope is much less steep. In other words, it's not angled up as much as cart number 1. This means that this cart is moving slower than cart number 1 because the steep is lower. The steeper the slope, the faster the object is moving. Secondly, keep in mind that if you do not have a slope, well then that means that that cart must be moving at a speed of 0 meters per second. It's not covering any change in position over the amount of time that is going by. Well, how can we tell which direction the cart is moving? Again, we want to keep in mind with what's going on with the slope, since the slope is telling us velocity. If the cart has a positive slope, as represented by cart number 1, 2, and 3, then that means the object is moving in the positive direction. A positive slope is angled upwards, meaning the cart is moving in the positive direction. For cart number 4, we have a negative slope. The slope is angled downwards. Its position goes from 8 meters to 0 meters over the course of 20 seconds. So the slope for cart number 4 is negative, therefore it has a negative velocity. It moves in the negative direction. How can we tell which of these carts are in dynamic equilibrium? Well, remember, dynamic equilibrium means that the cart moves at a constant velocity. Well, the velocity is represented by the slope, so a constant velocity is represented by a constant slope. Consider cart number 2. Notice that as 1 second goes by, that cart increases its position by, but as 5 seconds go by, that cart increases its position by 1 meter. And this holds true for the entire slope that is represented for cart number 2. 5 seconds go by, it increases position by 1. 5 seconds go by again, it increases its position by 1. That is a constant slope, and that is represented by a completely straight line. The same is true for cart number 4. As 1 second goes by, as 5 seconds go by, that cart changes its position by negative 2 meters. And that is going to continue for the entire slope of cart number 4. Well, how can we quantitatively read position versus time graphs? Well, remember, the slope of a position versus time graph is telling you the velocity. So if I wanted to know exactly what the velocity of these carts were over time, I would want to know what the slope was. Well, if we write this in equation form, we know that slope is found by doing delta y, the change in the y value, over delta x, the change in the x value. For a position versus time graph, your delta y value is actually representing the change in position. That is also known as delta x. Delta x stands for the change in position. Well, what do we have on the x-axis? We have time. So that is going to be delta t. So the slope can be found by doing the change in position over the change in time. And once again, we said that the velocity is slope. So therefore, an equation for velocity can be represented as v equals delta x over delta t. For this graph, this is the same thing as your equation for slope. So every time you want to find the velocity of an object, you can use this equation. For cart number 1, I can look at the slope of cart number 1 to figure out the velocity. Well, I know that cart number 1 changes its position. It has a vertical change of 8 meters, and that is my delta y. So v equals 8 meters over the change in time. Well, it goes from 0 seconds to 20 seconds. So the velocity is going to be 8 meters per 20 seconds. In other words, 0.4 meters per second. I could do the same calculation for cart number 2. Remember, since the slope is smaller, we should end up with a value that is smaller than the slope for cart number 1. So this time we're going to do rise over run for cart number 2. I notice that it starts at a position of 2 and it goes all the way up to a position of 10. I can then go across to get the run. It goes from 0 seconds to 40 seconds. So for this cart, my change in y, in other words, my delta x value, the change in the position, is going to be 8 meters. My run is going to be 40 seconds. So for this cart, I have 8 meters over 40 seconds. Therefore, the velocity is going to end up being 0.2 meters per second. For cart number 3, we have a little bit of a tricky situation. Remember, we have this moment where the cart is not moving, and then we have the moment where the cart is moving. Well, the velocity for that first segment of motion is going to end up being 0 meters per second because there is no slope. Again, if I wanted to find the velocity for that second segment of motion, all I'm going to do is rise over run. The change in position of the cart is 6 meters over 15 seconds. Again, the velocity is going to be 0.4 meters per second. Now this makes sense because the slope is exactly the same as the slope for cart number 1. And if they have the same slope, they should be moving at the same velocity. Another thing we could do with this graph is we could get something called the average velocity. We're actually doing this with all of our calculations, but if we have something that's changing its speed over time, what I could do is I could look at the overall change in position over the total change in time. So for cart number 3, I could take the first position, the initial position, and connect that to the final position. Again, we are going to use the equation v equals delta x over t, but I'm going to use it for the entire time interval. For this example, we have a change in position from 6 to 9, exactly the same as before. We have a change in position of 6 meters, but this time we are going to consider the entire time of travel. In other words, the 18 seconds that it was traveling. So for this one, I have 6 meters over 18 seconds, which is going to give me an average velocity of 0.33 meters per second. Notice that this velocity is a little bit less than the velocity of the travel between 3 and 18 seconds. This is because we are averaging in a period where it wasn't moving. This is going to reduce the average velocity. For cart number 4, we have a pretty similar situation. Let's see if you can figure out the velocity for cart number 4. Well, once again, we're going to do rise over run, except this one's not really rising, it's actually descending, but we're still going to call that the change in position or the change in the y value on the graph. So for this graph, I have b equals negative 8 meters over my change in time, delta t, which is going to be 20 seconds. I end up with negative 0.4 meters per second. Well, how did the speeds of the carts compare? Well, just like we said before, the slope of cart number 2 was the least steep slope. So this cart, as shown in our calculations, is the one that is moving the slowest. The slopes of cart number 4 and cart number 1 are actually the same exact number, they're just moving in different directions. Therefore, we could say that cart number 1 and cart number 4 had the same speed, but they had different velocities because they are moving in different directions. Okay? Lastly, for your hallway carts activity, you were asked to represent the motion of these carts in slope-intercept form. We wanted to use an equation to represent the motion of the carts. Slope-intercept form is represented by y equals mx plus b. Well, you're going to apply the slope-intercept form anytime you have a linear fit on a graph. But this is just the equation that you use in your math class. Each of these variables have a specific meaning relating to the graph that you are looking at. For instance, the y-axis is representing your position. The slope, we said, was already representing our velocity. The x-axis is representing time, and we said that the y-intercept is representing our initial position. So this is a graph that really represents what is going on. This is an equation that represents what is going on with our graph. The x that you are seeing here is the final position. So the final position of an object is equal to velocity times time plus its initial position. You could think of this term, velocity times time, as being the change in position. In other words, if an object started with a specific initial position and it changed its position by this quantity, then it would end up at this final position you see here. Thanks for watching. Hope this helped.